Alrighty, there. So I'm going to go over this video, section 10-3 on regression, just continuing off of that correlation section. So key concepts in this section here is in part 1 of this section, we find the equation of the straight line that best fits the paired sample data. That equation algebraically describes the relationship between two variables. The best fitting straight line is called a regression line, and its equation is called the regression equation. There may be another name, I'll show you later. Then in part 2, we discuss marginal change, influential points, and residual plots as tools for analyzing correlation and regression results. All just kind of seeing how good a line fits some paired data, basically. Alright, so now for part 1. So in regression, the regression equation expresses a relationship between x, and sometimes this is called the explanatory variable, the predictor variable, or just simply the independent variable, like you may be more used to. And then y hat is called the response variable or the dependent variable. And notice this book uses y hat more so than just y, just to kind of distinguish that this y hat is a predicted value. Now, the typical equation of a straight line, y equals mx plus b, is changed and expressed in the form y hat equals b naught, or b sub 0, plus b sub 1 x, where b naught is standing for the y-intercept, and b sub 1 is the slope. Now, depending on what source you look at, different variables may be used here, but still they're standing for a y-intercept and a slope. Now for the regression equation, now when you're given a collection of paired sample data, the regression line, or the line of best fit, or the least squares line is that other name, and is the straight line that best fits the scatter plot of the data. And you'll see towards the end of the video why it's called the least squares line. And the regression equation, y hat equals b naught plus b sub 1 x, algebraically describes the regression line. Okay, so kind of just re-emphasizing some stuff there. Now, as for the notation, just know when you're describing population parameters using regression lines, beta can be used in place of b. Again, just continuing with the theme of Greek letters usually stand for population parameters. And then just for samples, we'll use our regular English letters. And now some requirements for our regression are similar to the correlation. So the sample paired data, the XY, should be from a simple random sample, quantitative data. Then upon visual examination, the scatter plot should show an approximate straight line. And then ultimately we want to avoid any outliers as much as possible. Now these are some formulas for finding that slope and the y-intercept in that equation. To find the slope, you can take the correlation coefficient, r here, and then multiply it by the standard deviation of the y values divided by the standard deviation of the x values. And in order to find the y-intercept, you need to make sure you have that slope first. You can take the y-intercept equals, so the average of the y values minus the slope times the average of the x values. Now, technology can also compute these values and still suggest using the same stat-semantic applets from the previous lesson, which I can show you again here how to find those. So let's go into the class and go on to pages, view all pages, YouTube and other tools, and come down to just the stat-semantic applets. And you can use just some of the same applets that were mentioned from before. So I'll be using the testing a slope one, but they all give you the same thing. Testing a slope, testing a correlation, or the linear regression t-test. All three can give you the same stuff. And just a reminder, in case you want to be doing the standard deviation by hand, this is the formula for a sample standard deviation. If you don't want to try and do things using just that formula, you can use this little table setup or something like this to kind of help organize it for you. Ultimately, just put the x values in here. You'll need the mean of those values, and it doesn't have to be x. I'm just using x in this case. Find the mean of those x values, then take the difference in this column, take those differences, square them in this column, then put that sum down in this box here. then your last steps would be to just plug in the sum divided by your sample size minus 1 and take the square root of that. That'll also get you your sample standard deviation. So just a little reminder. These are some other formulas that you'll find in your book for how to find the slope and y-intercepts for the regression line. Now, of course, these are a bit more involved, but of course, these are things that you can do if you want to try these out instead. And just make sure you're careful with using all this properly, depending on what the notation is. So, like for example, this is the sum of all the products of the corresponding x and y values, whereas this one is the sum of all the x values, then times all the sum of all the y values. Alright, another example where we'll get a regression equation. And so we're going to use the same example with shoe print lengths and heights from the previous section. And so we'll use as the independent or explanatory variable is the shoe prints, and then the response variable is the height. And so our requirement check is we're assuming this is from a simple random sample. When we look at our scatter plot, it's roughly a straight line, and then there are no outliers. Same stuff that we were using from before. Now, and again, the use of technology is recommended for finding the equation of a regression line. So these are some examples of technology you can use. You can use programs called StatDisk. You can use Microsoft Excel. You can use Minitab if you have a TA83 or 84 calculator. And then, but again, the applets that I'd recommend are some StatsMedic ones, just for our purposes. And I went ahead and used this testing a slope one. And I've got some of the data already plugged in here, just so I don't have to watch me type that. Again, I just click Begin Analysis. Gives me that scatter plot, roughly kind of straight. Now, see, I don't need the correlation, but I'll just go ahead and confirm it's that same correlation from before, 0.591. And now this time I can calculate the least squares regression model. So notice it's giving me the full equation now. So there's the y-intercept, and there's the slope for this one. And once I hit that, then it puts the actual line in there for me as well. And so when we look at that equation, the equation can be abbreviated decimal-wise as y hat equals 125 plus 1.73x. And again, that's the same formula, just different number of decimal places as this one that the StatsMedic applet generated. And so recall from the previous section, if we want to do this using the formulas, that again, that correlation coefficient was about 0.591 and just with some continued decimal places there. So it still matches up with this here from the applet. And then once we plug that into the formula, then this would be our standard deviation of the y values, so those heights. And this would be our standard deviation of the x values, so those shoe prints. So once we plug all that in, we get about 1.72745, which when we round it off, still comes out to that same slope there. And then we can plug everything in with that formula from before, not the long one, for finding the y-intercept. So this is the average of the y values minus that slope there times the average of the x values. Then that's how we get our slope there. Again, just a little reminder for how to find the standard deviation from sample values. So I just listed out some more steps here using like this table, if you like using that table for finding the standard deviation of the x values. So if you want to review this more, you can pause here. If not, I'll just go on. And so, and a graph of the equation and the scatter plot will look something like this, but we've also got that on our applet here. This is just generated by a different program. We can use the regression equation for predictions. That's one of the main purposes of regression in general. And so we use the regression equation for predictions only if the graph of the regression line on the scatter plot confirms that the regression line fits the points reasonably well. So if it just looks reasonable, then we use the regression equation for predictions only if the linear correlation coefficient R indicates that there is a linear correlation between the two variables. And so it's, again, just seeing if it looks like we have a good correlation coefficient relative to whatever our critical values are from the table 10 dash, sorry, from table A-5 for section A-2. So like for this one, depending on what significance level we'd use, we'd want our correlation coefficient to be bigger than 0.878. Say if we use 0.05 significance level, say there is good correlation. But for this particular problem, there is not good correlation. So we'll do something else for making a prediction. All right, then continue with that. So use the regression line for predictions only if the data do not go much beyond the scope of the available sample data. And so if you predict too far beyond the scope of the available sample data, it's called extrapolation, and it could result in bad predictions. And so just an example of that just means, like, say I used this data here in that line to predict the height of someone who had a shoe length of 60 centimeters. That'd be like way out here, and that wouldn't be a very good prediction. It'd be very extrapolated. And if the regression equation does not appear to be useful for making predictions, then your best predicted value of a variable is just one of the sample means, so the y sample mean. And again, just a little chart here kind of emphasizing that same idea. See if the regression model is good, there's good correlation, so you can actually use the regression equation. If yes, great, go ahead and use it for making a prediction. If not, use the sample y mean value. All right, and then if the regression equation is not a good model, again, just use the sample mean of y. And remember, this strategy applies to linear patterns of points in a scatter plot. Now, if the scatter plot shows a pattern that is not a straight line pattern, then other methods can apply that are in later sections, but we won't be getting into those sections. So, for example, using that same set of 5 pairs of shoe and height data, then we're going to use that to predict the height of a person with a shoe print length of 29 centimeters. So since, again, that regression equation was not very good, not a good correlation coefficient and such, then our best predicted y value would just be the mean of the y values from our sample, which is just 177.3. Now, for another example that actually does have good correlation, using that same pirates versus global warming temperatures example from the previous section. And so, again, you can see that it looks like this is following a roughly straight line pattern, and we're assuming this came from a simple random sample, and we don't see any major outliers of pirates or temperatures here. And let's see, just to reemphasize, again, I've got that data plugged into another one of the applets here. So if I go and click Begin Analysis, it gives me that scatter plot. Just reconfirm that correlation coefficient is a good one of negative 0.926. And then when I calculate my least squares regression line, then here's the line that I can go ahead and use. And but just this other information is just sample size, then the r-squared value. Don't worry about S here, that's the standard deviation of the residuals, which I'll explain what the residuals are in a little bit. But since this one did have a good linear correlation, we can go ahead and use this equation for making predictions. And so, just as an example, use this model to predict the global temperature for when there are 42 pirates. So basically, I just plug in 42 for x into that equation, since 42 is the explanatory or the x variable. And once I plug all that in, I come out to about 15.5 with some extra decimals for the y value. So basically, the temperature would be about 15.5 degrees Celsius after using that equation. All right, and then let's see, I'm going to save the rest for the second part of the videos.